So the first question is about diffraction, and diffraction is a relationship between a wavelength and a gap. Now, the best way to remember this is to remember sound. Sound has a very large wavelength, and if you think about yourself standing at a doorway, you will be able to hear someone around the corner if there's a door in the way. So if you're standing over here and this is the door, the sound will diffract. Why? Because sound is large. It has a large wavelength. So large wavelength through small gap would give you diffraction. Now, funnily enough, this question isn't about this. It's actually just asking you to pick out a realistic shape. This is a realistic shape because the wave is not changing. The wavelength is not changing like it is here. There's no reason why the wavelength would change just because it goes through the gap. And it doesn't need to spread quite so urgently in that way. All you're getting is the wavelength in the center continuing unaffected, yet curving slightly on the edges. Okay, so the answer is A. Question B, similarly, what you're seeing here are some really unrealistic pictures of diffraction. Now, with obstacles, when you have a large wavelength, you're more likely to get diffraction. And the answer here is B. But it's B simply because of the definition. Firstly, this is not diffraction. This is completely compensating for the gap. This is almost as if there was no gap in the way. These curves are completely unrealistic because they're not gentle curves. They're literally a wavefront changing direction, so they're too sharp. And this one's wrong because the wavelength has changed after the obstacle. There is no reason why the wavelength would change. So this shows a bit largish wavelength, so it's going to get some spreading. And then you have no change in the wavelength, so therefore that's a realistic situation, and the curving is slight on the edges. In order to answer questions on refraction between two boundaries, the best thing to do is to remember the experiment that you did in class. Let me talk you through it. In your experiment on refractive index, you had a boundary between air and glass. The light came in from air and went into the glass. Now, what you have to remember are the results of this experiment. The ray of light came in at an angle and bent closer to the normal. So if you remember that the angle is smaller in denser material, and you remember this shape, the bending towards the normal, then it doesn't matter what the question's about, even if it's in the opposite direction, okay, you'll be able to remember this order. If you're going into dense material, it bends towards the normal, and if you leave, if it's the other way round, and you have an incident ray coming out, it bends away. Okay, so going into dense towards, going out of dense material, it bends away from the normal. So let's look at the questions now. As we can see here, question 3 shows a plane wave approaching and passing through a boundary between two different media. The speed of wave 1 is greater than v2. So v1 is greater than v2. So let's analyze what that means. If it's going faster through v1 than v2, then the material 1 is less dense than in v2. Remember, the reason why a wave would slow down in a medium is because it's denser. And just think about, the wave trying to pass through a denser material will definitely slow down. Okay, so the medium 2 is the denser material. So really, we're just looking at a question which is very similar to the initial experiment you did in refraction in class. Now, what is the relationship between a wave front and a ray, an incident ray? Well, the ray is actually at 90 degrees to the wave fronts. If you can imagine like an ray of light magnified 1 billion times, if you could look at it, you would see the crests traveling in a perpendicular direction. So they would be along the lines like this. So your incident ray is at 90 degrees to the wave fronts. So what happens inside the glass? Well, your incident ray bends towards the normal. So you've got to see wavefronts that bend in such a way that they would represent this. And it could either be A or B. The problem is, in B, you've got this curved situation, which definitely would not happen. There would be no other change to the wavefronts apart from this slight change or shift towards the normal. So the answer is definitely A. Okay, because there's your incident. Bing. Let me try that properly. And there you go, that's much more civilized. So you can see that there is a shift towards what would be the normal here. Okay, so this angle is definitely bigger than this one. So the answer is A. Similarly, question 4 is pretty much asking the same thing. Sound waves move faster in warm air than in cold air. So warm air is less dense than cold air. The diagram shows the plane waves in cold air moving towards a boundary with warm air. So this is like the reverse of the situation I was talking about before. So instead of it coming in and bending towards the normal, what we've got instead is it comes out bending away from the normal. So if this is our ray, which is the wave that bends away from the normal, well, 1 bends towards, 2 continues along the same line, so it must be 3, which is answer C. Okay, for exactly the same reason as 3. Now this one, number 5, is more just factual recall. When a wave crosses the boundary between two media, which one does not change? Well, amplitude changes because energy is always lost. It is a process called attenuation that we'll look at in the topic, but generally you should know that anyway. Amplitude is related to energy, so therefore as it loses energy, and that would happen in any situation. The wavelength, if you remember, the velocity changes, the speed changes, the wavelength changes, so D and B and A all change, so therefore the answer is frequency, because the nature of the wave stays the same. Okay, so that's just something you're going to have to remember. Frequency always stays the same during refraction. Here we have a wave trace, and remember, these are very common questions. You have one wave which has time on the x-axis and one that has displacement on the x-axis, so they're different. What is meant by travelling wave? If you remember, we're talking about the transfer of energy, energy being the magic word. And how do we know it's just one magic word? It's one mark. So a travelling wave, as opposed to a stationary wave, transfers energy. Now I'll stay on this page to answer the following questions. The amplitude, how do we find the amplitude? Well, you can find the amplitude from either graph, because you have, as you know, the amplitude is from the center to from the equilibrium to the crest or the trough, and you can measure that on any of them. You have 4, but please remember to check the axes on these kinds of questions, because they always sneak some funny value in. The answer would be 4 millimeters. Okay, so be careful with that. The wavelength. Now, wavelength can be measured directly from a displacement graph. Okay, so what have you got here? If we have a look at an entire cycle, starts here and ends here. So what we've got is 2.4, but careful, centimeters. So you've got 2.4 centimeters is your wavelength. Okay, so it's very easy to make that mistake and just write 2.4. Frequency. Now, the frequency can be worked out from this graph, which is a displacement time graph. So you should remember that frequency is 1 over the period. And we can easily read the period on this graph. So here it is a little bit tidier. We've got one entire wave that begins here and ends here, and it's 0.3. And have a look, it is seconds, no funny business there. So your frequency would be That's your t. So your frequency would be 1 over t, which equals 3.3 hertz. Please start thinking about your significant figures at this stage. Because all of these values are to 1 decimal place, then you need to be as appropriate. Now, last one. The last one we have to work out is the speed. Now, this is where your attention to detail is important, and by detail I mean units. So the speed would be the frequency times the wavelength, the frequency being 3.3 per second, and your wavelength was 2.4 times 10 to the minus 2, because it was in centimeters. Okay, so you would end up with a value of 0.08 meters per second, right? Which you could say 0.79 was also okay, but it's actually 0.0799, so you do round it up to 80. Okay, so that's this question done. Now this is a lovely question. The diagram below shows a plane wavefront incident on a boundary between two media. You have a ratio of refractive index of B, right? So I'm going to call it 1 and 2, because that's the way we've discussed this in class. So what they're giving you is the ratio of N2 over N1 equals 1.4. What other information do they tell you? The angle between an incident wave front and the normal is 50 degrees. Now this is horrible, because they're not saying that the incident angle is 50 degrees. No, that'll be too easy. They're actually being really cruel. They're saying that this angle is 50, right? Because this is a wavefront and this is the normal. So they're saying this is 50, which is horrible. Now, if this is 50 degrees, what you need to then see is that if this is our incident ray, this would be 40 degrees. But I can't tell you how many people just instantly assumed that the incident angle was 40 degrees. Okay, but listen, be aware of this. It could crop up again. So let's go back to where we were a minute ago. We have N2 over N1 is 1.4. Now, calculate the angle between the refracted wavefront and the normal of the boundary. So what we're looking for is, oops, let me draw it properly. Okay, so we need to find that angle there. Now let's think about Snell's law. We have sine of 1 over sine theta 2 equals V1 over V2 and equal to N2 over N1. So in effect, sine I1 over sine theta 1 over sine theta 2 equals 1.4. How do we know? Because that's the information we've been given in the question. Okay, so once you've got that, just rearrange this, substitute in your value for I'm doing it myself now. Substitute your value for 40 in here, okay? And you can work out that your angle is 27 degrees. Okay, so that should give you 27. But this is how mean they are. They're not asking you for this angle. They're asking you for the refracted wave front. So once again, you have to do this silly business. 90 minus 27 degrees, which gives you 63. Okay, it's pretty mean, but that's just the way it is. So what else are they asking for in this question from hell? It says, construct 3 wavefronts to show the refraction of the wave at the boundary. So you're going to have to continue these lines to show refraction. So what I suggest you do is you first draw the incident ray as it should be. So if I draw normal here and then draw it bent like that, and then what you do is you put your ruler, you continue from here, and you make sure that you draw lines which are at 90 degrees, like that. Okay, and then you do the same here at 90 degrees. Now, remember, these must be parallel, and they will be, I mean, these two will be anyway, if you draw them properly with a ruler, but they must be closer together, because remember, the wavelength gets smaller inside the denser medium. Okay, so it should be like this, but properly done with a ruler and a pencil, a sharp one. That would be great. Okay, so that's that question. This is a less mean question, but it's similar. The diagram below shows 3 wavefronts incident on a boundary between medium 1 and medium R. Okay, wavefront CD is shown crossing the boundary. On the diagram, draw a line to complete wavefront EF. So EF, so basically you need to make sure that it's parallel to this one. Okay, so you would just get a ruler and you would try and draw as closely as possible a line which is parallel. Not like this one, which is rubbish. Let me do it again. There you go, that's much better. Explain in which medium the wave has a higher speed. So you should be able to gauge that the wavelength here is, let's have a look, medium R is less than in medium L, I think. Is it an L? Yeah, okay. So medium L. So therefore, this one is going slower. And if it's going slower, it must be denser. Okay, so which one has the highest speed? In medium L, because wavelength in L is bigger than wavelength in R, because the speed in L is higher than the speed in R, and V equals lambda F, where frequency is constant. Now that's a pretty full and complete answer. So what's this question about? The graph below shows the variation with time t of the velocity of one particle of a medium through which the wave is travelling. So how can we tell that the wave is oscillating? And I'd like to apologise on behalf of the IB for asking such vague questions, but sometimes you just get stuff like this. How do we know it's oscillating? Because you have an equilibrium position, and there is displacement and velocity in opposite directions. Okay, so first it's going plus and then it's going minus. So I guess that's the definition of an oscillation, that you start an equilibrium and you displace on either side of that equilibrium position. Okay, if we check the mark scheme, that's pretty much what it says. Determine the frequency of the oscillation of the particle. Again, it's a bit repetitive. You should remember that F equals 1 over D, period. And the period is the time for one full wave. So what have we got here? We've got 3, but what's the catch? 1 over 3. The catch is what's on the x-axis times 10 to the minus 3, because it's milli. Okay, so our answer there would be 330 hertz. That's better, you can read it now. Now mark on the graph with the letter M the place where the particle is at a maximum displacement. This is in effect a motion, a kinematics question. Now you should remember, and I hope you do, that there is a relationship between a velocity time graph and its displacement. If you have a velocity time graph, the displacement, this is a VT, the displacement is the area under the graph, and the other side, if you have a displacement time graph, your gradient would give you the velocity. Now, just because this happens to be a simple harmonic motion question, it doesn't mean that that's still not the case. We still treat it in the same way. Now, where is the particle, at which point is the particle at maximum displacement? So if we think about the displacement time graph, and there is a displacement time graph, what exactly is going on at maximum displacement? Well, at maximum displacement, there is something kind of interesting going on with the slope, right? The slope is equal to 0. So the velocity must be equal to 0. So let's go back to our original velocity time graph. Where is the velocity equal to 0? At the origin, and we're going to put an m there, or we can put an m here, or we can put one here, or we can put one here, or we can put one here. But I think you get the idea. So it's where the velocity is equal to 0. Right, the next question is to estimate the area between the curve and the x-axis between t equals 0 and t equals 1.5. So here and here, basically. So it's a count the squares moment. Now there is a number of ways that you can do this. If there isn't a considerable amount of squares, you could literally just count the small squares. Because you will be hard pressed for time, it might not be the best way to do it. So let's have a look at I'm going to look at bigger squares. See that square there? What does that actually represent? That's the first thing you're gonna have to work out. Now it represents this side. It's a square of side length 2 times 10 to the minus 3. Again, remember the sneaky axes units, right? So it's 2 times 10 to the minus 3. And then here, what does this represent? This represents 0.5 times 10 to the minus 3. So if I multiply those two values, right, I get the value of 1 square. And then all I have to do is work out the number of squares. So we've got 1 here, oops, 1 here, 1 here, 2 there. Then we've got 3, but it's not quite full. But I'm going to count it as a 3, because if I count that one, then it will include that bit and that bit. So I've got 3, which leaves these two, which are kind of almost 1 and a bit, and this bit, 1 and a bit. So I've got 1, 2, 3, 4, 5, approximately. So let's see how we go with that. So the total area would be 5 times 0.5 times 10 to the minus 3 times 2 times 10 to the minus 3. Now the range of values that is acceptable is anything between 5.8 times 10 to the minus 3. Oh, actually, it's even more generous than that. It's 5.6 all the way to 6 times 10 to the minus 3. So all of these values, anything between this range, would be considered an appropriate value for the area. Now, what does the area represent? Well, let's think about this distance time graphs again. Okay, so this is a sort of displacement time graph. And what have we got here? Here we've got velocity 0. Well, as we spoke about before, the reason why velocity is 0 is because the gradient here is at a maximum. So displacement is at a maximum, and that gradient is positive. So it's on the positive axis. Now, you've worked out the area from here to here. So I need to figure out where is the object when we get to this point. Now, this is 0 again on V, which means it's a maximum again for displacement, but in the minus direction. So what we've worked out by working out all this area is the distance from here to here, which is the distance from here to here, which if this is the maximum displacement, that is the amplitude, and then this is the amplitude again, so it would be 2 times the amplitude. And this question stretches on forever. State the principle of superposition. So this is just a learn it off by heart question. What do we mean by superposition? The resultant displacements, actually I'll just read it out. Resultant displacements equal the sum of the individual displacements. Okay, so you can just learn that definition. Let's have a look at an interference question itself. We have 2 loudspeakers, S1 and S2, connected to the same output frequency generator placed in a room as shown below. Sound waves of wavelength 40 centimeters, right? So that's your wavelength, and amplitude A are emitted by both loudspeakers. M is at a point distance 550 centimeters away from both S1 and S2. Point P is 560 away from S1 and 580 away from S2. It's a lot of information. Let's try and make some sense of it. So what happens as you move from P to M? Now, you guys actually did this, so you know there's going to be a change of amplitude. And there's a change in amplitude because you get constructive and destructive interference. Now, your constructive interference is when waves are in phase. Destructive, when they are out of phase. Okay, so when you have that situation. Now let's have a look at what's going on here at M. M is 550 centimeters away from S2, and it is also 550 centimeters away from S1. If you're not sure of that, reread the question. It says it here. Now that means that they reach point M in phase because you've got exactly the same number of wavelengths between S1, M, as you do between S2 and M. Okay, so you're getting constructive interference. This is called a maxima, and it means that it's very loud. Now, what's going on at P? You've got 560, so you've got 560, which is a number of wavelengths plus a little bit, and then you've got 580. Now, if we subtract 560, oops, that's better. So if we subtract 560 from 580, we're left with 20. That means that this wave is 20 centimeters bigger than this one, which happens to be half a wavelength. Now, if we look at half a wavelength, that means that when the crest of this one arrives, the trough of this one arrives. They are in antiphase. You've got destructive interference. So what you've got is a quieter part. Now you could argue, well, it should cancel out completely, but it doesn't because sound bounces along the room. There's always some kind of like input of sound at that point that's not just from these two. So you'll never get like it dead silent, but you definitely find that the volume, the amplitude is much less. So as you walk from P to M, the amplitude increases to a maximum at M. Now, what would happen if S1 suddenly releases waves that are much bigger in amplitude? Okay, well, you would still get, like an M, you'd get exactly the same situation as before. You'd get constructive interference, but you'd just be louder because not only would your two waves add up, you would also have the fact that one of them was twice as big anyway. So if you're going to get constructive, you're still going to get constructive, and your amplitude is going to be, well, twice this one plus this one. Okay, so it's going to be louder as M is still constructive. And then a P, it would still loud, but you won't get this totally destructive situation because some of the wave would cancel out. They're in antiphase, so one and the other would cancel, but because one of them, S1, is releasing waves of a much bigger amplitude, you'd still have some left over. You wouldn't have them cancelling out completely, so it would be louder at P, but much, much louder at M. And you would have to explain the fact that they're still constructive here and still destructive. It's just that the amplitude is bigger for both. The loudspeakers are replaced with monochromatic light source. State the reason why you won't get this bright and dark fringes situation. Well, if you remember the laser experiment that we used, you don't use two lasers, do you? When you're trying to do two source interference, you must have one monochromatic light, one source. In fact, you do have it in sound because loudspeakers are simply one source, a signal generator. Okay, so you'll have a generator which is generating the sound, and then they're just being released by two loudspeakers, but the actual origin of the sound is one. If you try and do the slit separation experiment with light, you would use one laser but two slits, and the diffraction would act as if it was two single separate sources. So it's monochromatic, tick, but they're not coherent, which is what you're guaranteeing if you only have one source. Okay, so this question ignore because it's high level and I haven't even taught them this yet, so you can ignore that. And let's go on to the home stretch, the last question, which is an easy peasy one at the end. Which one of the following graphs shows the wavelength and the amplitude of the wave? And I'm hoping, I'm praying, that you all got D as the correct answer because it's an easy peasy question. Okay, that's that for now.